Hey everybody, welcome back to Organic Chemistry, and now we're doing Chapter 13, Part 2. So at this point, I hope that you watched the videos for Part 1, and that should give you a really good understanding of conjugation, orbital systems, stability of conjugated systems, and a whole bunch of other details, right? Like UV visible spec and so on. Well, now it's time for the reaction. So now we're going to dig in deep and figure out how these conjugated systems react in the real world. And so we're going to go through that right now. Now, let me just tell you, so for this particular video set for Part 2, we're going to first start by doing a review of the organic 1 reactions that are important. Not all of them, because there's way too many, but we want to remind ourselves of the ones that are really important for this chapter. Okay? We're going to add to that NBS, which is a specific reaction that we'll talk about. We'll go over the conjugated addition and also conjugated substitution, which I have categorized as similar reactions. Then we'll do the Diels-Alder reaction, and we'll learn about all the different details related to it. It's really not a hard reaction to learn, but it just takes a little bit of practice, and usually it's one that everybody loves on the exam, because once you get it, you get it. And it's, pretty straightforward once you got it. So the last thing we're going to do is the symmetry forbidden and symmetry allowed reactions, and we'll figure out how orbitals will tell us whether a reaction could take place or not. Okay, and that's basically what we're going to cover for this second round, for Part 2 of Chapter 13. So the first thing we're going to do, number 1, is we're going to do a review of 321 reactions. Okay, so Organic Chem 1 reactions. And in particular, we want to focus on reactions with alkenes, because that's what this chapter is all about. It's conjugated systems, right? And so the first one I want to talk about is HX, and of course is hydrogen halide, and how it reacts with an alkene. So there are certain things we have to remember, and this is in particular one for sure. Okay, so remember that when you have HX, it could be HBr, HCl, so X could be any halogen, Br, Cl, I, F, so on. And so what happens is the double bond winds up pulling in the H. And remember that when you have a difference in degree, we always make the higher degree carbocation for stability, right? And so we put an H on the lower degree so that the higher degree, secondary in this case, becomes positive. And then Br will come in. Now, we don't have to worry too much about rearrangement right now, but we know that there's always methyl shifts and hydride shifts if it's possible, right? But for now, we just want the general reaction mechanism, and this is it right here. So what's important to remember is that if you have HX, you break an alkene double bond, you put in the H first and then the X second, right? X being Br, Cl, I, or F. Now, the second reaction I want to review is specifically HBr, but it's in peroxide, okay? So this is going to make a different result set by having it in peroxide. Now, if you remember, this is a radical pathway. Now, we don't have to go into all the steps of initiation, propagation, termination. You're never going to have to do that again, okay? But what you need to remember is the general idea. And the general idea is like this. When this bond breaks, the Br comes in first, right? So the alkene attacks the Br and the Br makes a bond, but it does it first. And this is the difference between the top and this one, is that Br instead of H comes in first. So just like H went to the low degree, Br goes to the low degree, okay? But the carbon that's high degree, instead of becoming a carbocation, it's going to become a radical. Okay, so that's the intermediate, a radical. And now once you have this radical, then the H radical that you formed during this first step will then go into that position that's the carbon radical. So you wind up getting an H right there. Now you don't have to really show it, so I'll just erase that. But you know the H goes wherever the radical is, okay? And so this is HBr and peroxide. This is X can only be Br, okay? So this doesn't work with all the other ones. It has to be HBr. But what we found was that with this reaction, you could reverse and put the Br on the lower degree rather than the higher degree. And that's the difference between the first two, okay? So that's number 2. And again, this is all review. You should be familiar with these reactions, but don't drive yourself crazy with every small detail, because you're not going to need to know every little detail, okay? Now, the next one is halogenation. Now, with halogenation, that's where we're dealing with X2, and X could be Br, Cl, I, F. Now, last semester we learned about combinations where you put a Br and a Cl in instead of Br2 or Cl2. It could be BrCl. But we're not going to have to really worry about that so much. So it's really just a general idea that you have, let's say, Br2, okay? But it could be I2, Cl2, F2, and even combinations, okay? Now, this is usually in CCl4, but again, I wouldn't worry too much about what it's in. Let's just focus in on the Br2. Now, what happens is you break this double bond, and now last semester we were told that the Br makes this triangle, like that, this bromonium ion, and then the second Br comes in, or whatever the halogen is, it goes to the higher degree. So here's the primary carbon, secondary. So Br goes secondary, and this opens up to the primary. So we wind up with the Br here and here, anti, okay? Now, what I want to point out from this is that for this particular chapter, even though the Br is a triangle, we tend to not even consider it that way. We think about the Br on that carbon here and really not connected to the secondary carbon. And you'll see why when I get to that part with the conjugation. But just this is the general mechanism that we're looking at here. This is what you should remember from last semester, okay? Now, another thing that we talked about, number 4, is X2 with heat, okay? Halogenation with heat, okay? Now, actually, let me write it like this. Halogenation with heat or light. Okay, this was chapter 10, where we learned about radical reactions. And what we found was that if you have Br2 or Cl2, it doesn't matter what the halogen is, but if you have, let's say, Br2, and there's heat or light, I'll use light, then what winds up happening is we get a radical pathway to take place. So we wind up getting a radical formed on the carbon next to the double bond. Remember, this is called the allyl position. It's the carbon that's next to a double bond. That's not a double bond itself. It's sp3. Okay? And the allyl becomes a radical. And we talked about why that's so stable, and it's because of resonance, right? You have resonance stabilization. Well, when you make an allyl radical, then the Br radical, or Br2, will be attacked. So this gets pulled in, and the Br goes there. So with heat or light or heat, right, you wind up getting a Br next to the carbon that's double bonded, okay? Without the heat, without the light, you get attached, or the addition product where the Br comes in twice. So this is a difference. So I'm trying to point out the most important differences and things that you have to recognize. Now, we'll find out that number 4 is actually a bit of a problem, but we're not going to talk about that until the next section, NBS, okay? So for now, we're going to leave it like this. Now, number 5 is going to talk about acid-catalyzed hydration, so H plus H2O or ROH. Now, remember, if you have an alkene and you treat it with acid, let's write H plus. Remember, H plus can equal any acid, H2SO4, H3O plus, right? The H plus is a generic way without specifying the exact acid, but we know of some specific, like these two here, okay? Now, if we have an acid, we break the double bond, just like we did with HBr. We make a carbocation, always on the higher degree. So the double bond carbon is primary on the right, secondary in the middle. So we make a secondary carbocation, and then water or alcohol, depending upon the solution, will come in. So in this case, I'll use water. Water comes in, and then we wind up having OH here. And now, if you remember, initially when it comes in, it's going to have 2 H's on it, right? Water comes in with 2 H's. So we write step 2 minus H plus, just so that we can remove the extra H from oxygen. We don't want 2 H's on oxygen. And so we write minus H plus, and that allows us to just simply draw it out without the extra H. Now, we don't have to worry about showing the step, and especially this semester. We already learned all about it last semester, right? Minus H plus. So That's basically what happens. Now, if I happen to have H plus with an alcohol, then instead of OH forming, after this is a cation, alcohol comes in, right? And so you wind up getting OCH3. Now, initially it has an H on it, so we write step 2.